Okay, so I'm going to do a brief overview of linear regression with an example. Alright, so what we have is when we're doing linear regression, we have ordered pairs. And if we graph those ordered pairs, let's say we have x1, y1, and another ordered pair, let's say x2, y2, and then another ordered pair, let's say x, and let's say we go all the way out to n. We have n ordered pairs, so this would be xn, yn, right? So there's a bunch of ordered pairs here represented by only these three. What we really want to do is we want to find a line, the best fit line, so that when we draw this line, it minimizes the distance from the line, vertical distance from the line to the observed ordered pairs. So we want to find the straight line that has the minimum value for the sum of all these differences, or the squares of the differences actually. So that line is called the best fit line, and that line theoretically would be called y equals, it would be beta, the Greek letter beta 0 plus beta 1x. So that's beta sub 0 plus beta 1x, where beta sub 0 is the y-intercept and beta is the slope, or beta 1 is the slope. And we're going to be estimating these two things, but we're going to be estimating a third variable also called rho. Rho is the correlation, and it tells about the linear correlation, I should say. So basically, the value of rho is between -1 and +1, and -1 means a perfect negative linear relationship, meaning as x increases, y decreases, and the points fall on a straight line. +1 for a correlation coefficient, or for rho, means there's a perfect positive correlation, meaning the slope is positive and the points all fall on the same straight line. So this correlation coefficient ranges between -1 and +1. 0 would mean no correlation. Anything close to -1 indicates a strong negative correlation, and anything close to +1 indicates a strong positive correlation. So we won't actually know this equation or what this coefficient is, so we're going to come up with estimates. Our estimate for the y values, those are going to be called y hat, and the estimate of the y-intercept, instead of beta, we're going to use b sub 0, and the estimate for the slope, instead of beta 1, we're going to use b sub 1, and our estimate for the correlation coefficient, instead of rho, we're going to use r. Okay? So these are the things we're going to estimate. We're going to use Python to come up with estimates of all of these. But then even after that, we're going to come up with a p-value for this. And we're going to test a hypothesis. The hypothesis we're going to test, the null hypothesis, is going to be that rho is equal to 0, meaning that there's no correlation. And we're going to test that against the alternative hypothesis that rho is not equal to 0, meaning that there is a correlation. Now, that's going to affect how I estimate the values of these ordered pairs. I'm going to be given an x value and asked to estimate a y value from the data set. So they're going to give me an x and ask me to estimate what the y value should be. Now, depending on whether the correlation coefficient shows that there's a linear correlation, we're either going to use y bar, the average y value, or we're going to use y hat, the value that comes from the linear regression. And that all depends on whether we reject this null hypothesis or fail to reject this null hypothesis. If we reject this null hypothesis in favor that there is a correlation, then we're going to use y hat as an estimator. But if we fail to reject the null hypothesis, and the assumption is that there's no correlation, that means this would be useless, and the best estimate would actually be y bar, the average y value. So if we fail to reject the null hypothesis, we'll use y bar as our estimate. If we reject the null hypothesis, we'll use y hat as our estimate. So now we need to know how to find those things. So here's the example I promised. So we have a data set that we can download by clicking here. And then it wants me to come up with this regression equation, the value of R, the estimate for the correlation coefficient rho, the p-value for R, and it also wants me to come up with an estimate when x is equal to 24 at a significance level of 10%. All right, and then if you click this, it'll show the data here. So we have xy as our data, xy ordered pairs 389 and so forth. All right, let's go ahead and download the CSV of that data. Here's the download link. Click it and it downloads. And now I'm going to use Python to import this downloaded data set to Google. Once the file is downloaded, we come over to this folder in Google Colab, this file folder. We click it and we're going to upload the file we just downloaded to our computer to session storage. So here it is. We have correlation 1. This is the one that I just downloaded. And then it's now available, correlation 1 here. Let me delete this old one. So this is the file that I just downloaded, correlation 1. And I'm going to copy that path. And now I'm going to use pandas to import this, or to load this into a data frame. So I'm going to import pandas first. Import pandas and give it the nickname PD. And I'm also actually going to import, or I'm going to from SciPy, I'm going to import stats, because stats is actually where the linear regression method or function resides. So now I'm going to create the data frame df equals, and then I'm going to use pandas, which I called pd dot read underscore csv, and then I'm going to make a parenthesis and open up a quotation and paste the file path that I just copied to correlation 1. So there's where the file is, and I'm just going to take a look at the head of this data frame. So df.head will show me the head of this data frame. When I run this, this is the data frame that I just saw. All right, so now that I have the data frame loaded into Python, I'm going to go through now and I'm going to actually create this linear regression using SciPy stats. So here's how it works. It's going to give me a value for B1, the slope. It's going to give me a value for B0, the y-intercept. It's going to give me a value for R, the correlation coefficient. It's going to give me a p-value, and it's going to also give me a standard error. We don't really need the standard error, but it's going to give it to us anyway. And this is going to be equal to, and now I'm going to call stats dot lin regress, R-E-G-R-E-S-S, this one right here, lin regress, and I'm going to open up my parenthesis, and the first variable I'm going to have in here is the data frame bracket x variable. So x, I'm just going to select x, or you can just type quotation x. Then I'm going to make a comma between that one and df data frame bracket y. So now this will create the linear model for x and y from my data frame when I run it. So all I want to do now is I want to print these out. So let me see, I'm going to make a print statement. And in the print statement, the first thing I'm going to print out as a string in quotation is going to be B1, which is the slope. So I'm going to say slope equals, and then I'm going to add to that the string version, str, the string version of B1. So it's going to convert the variable B1 that function creates into a string and add it to the string slope equals. Going to do the same thing for the y-intercept. So the y-intercept is B0. So print here, And instead of slope, I'm going to do here y-intercept, and instead of b1, the y-intercept is b0. Then I'm going to do again, oops, I got rid of one of my parentheses there. Then I'm going to do again the same print statement, and the next thing it's going to print is going to be the value of r, the estimate for the correlation coefficient rho. So r equals, and then I'm just going to let it print r. And the last thing I want it to print out for me is the p-value. So I'm going to copy paste, and then I'm going to type here p-value. Alright, and then this will be that thing that I call p-val. Alright, when we run this, it's going to give us those four things. There they are right there. So now I can create my linear model that this thing is asking me for. Let's see, we have the slope of the line is this, and it wants us to round to 3 decimal places. So let me see here. I put the slope of the line, and then to the 3rd decimal place, that 8 would become a 9, and that's multiplied by x, and then plus the y-intercept. This is the value of b right here. And once again, round it to 3 decimal places. So I would actually need that 6 to become a 7, and there you go. That's the regression equation, mx plus b. Then it asked me for the value of r. Once again, this is the value of r right here. Rounded to 3 decimal places, it would be that value. Then it asked for the p-value. Well, the p-value is given right here. I want you to notice this p-value actually has this scientific notation, meaning this is 14 zeros and then 519. So that's times 10 to the negative 15th power is what that means. So if you do 5.19 times 10 to the negative 15th power, well, that's going to be a decimal point, 14 zeros, and then a 519. That's very, very close to 0. And if you round it to 3 decimal places, it's actually just 0. All right, so then it says at a significance level of 10%, find the best estimate for y given x is equal to 24. All right, now I know that if I reject the null hypothesis, it means that there probably is a correlation. And if I fail to reject the null hypothesis, it means there's probably no correlation. The criteria that we use is if the p-value, this number, is less than or equal to alpha, this number, we reject the null hypothesis. 0 is indeed less than 0.1, so we do indeed reject the null hypothesis. Because we reject the null hypothesis, we're going to use y-hat as our estimate. We're actually going to use the regression equation because we're rejecting the hypothesis that there's no correlation. We're rejecting this hypothesis right here of no correlation in favor that there is a correlation, and when that's the case, we're going to use y-hat. Okay, so now I'm going to calculate y-hat with this value 24. So I'm going to use this value 24 and plugging it into the linear regression equation. All right, so 24. So I'm going to calculate the value of y-hat, and it's going to be equal to, well, let me see. B1 is my slope, so this is going to be B1 multiplied by the x value that they gave me, 24, not 25, and then plus the y-intercept, which is b sub 0, b0. So this will give me the value of y-hat, slope times 24 plus the y-intercept, mx plus b. And I'm just going to print y-hat and run it. And this would be the value of the estimate. This would be the value of the estimate. And what they want, round to 1 decimal place. So I was right. 1 decimal place would be this. Now, on the other hand, let's say, theoretically, that the p-value wasn't so small and we had failed to reject the null hypothesis instead of rejecting it. In that case, we would have had to give, instead of y-hat as the value for the estimate, we would have had to give y-bar. And the way that you find y-bar is just the average y value. So what you can do if you fail to reject the null hypothesis is you can import numpy as np, and then you can use np.mean for the y values, just open a parenthesis and do df bracket and put the y values in there. And when you run this cell now, it'll calculate the mean of the y values of the data frame. So in the case where we had failed to reject the null hypothesis, we would have used this value for the estimate. But because we rejected the null hypothesis, that means the regression equation was in full effect, and we use this value instead.